And the visual cortex is back here, and then the auditory cortex is about here. And then the part of the brain that you use for silent reading is where the auditory and the visual cortex overlap. So that's pretty cool. So what it means is that you look at words and you hear them, because your eyes are using the auditory cortex as a representational structure. So that's pretty cool. And so it turns out that people who silent read pretty much use the same brain area to do that. And so you might think about that as biological preparedness in some sense, but of course people didn't learn to read silently till 500 years ago, roughly speaking. You know, even the earliest literate people, most of them read out loud. Silent reading was a very, very rare phenomenon. Julius Caesar could read silently, and people thought that that was part of his magical power. Because it's pretty damn weird, you know, that you can use your eyes to hear. You know, because you can all do it. You think, yeah, anybody can do that. But, you know, it's a pretty new thing on the evolutionary horizon. And to be able to hear with your eyes, it's like, good work, guys. That's not an easy thing to manage. So anyways, the brain has specialized subsystem, but it's a dynamic biological system, so you can muck about with it quite a bit, and it'll set itself up in slightly different ways. So the systems aren't necessarily localized exactly the same place in everyone, but roughly speaking, everyone has those systems, and roughly speaking, they're in the same place across people. Now, there's a lot of variability, and it's one of the things that makes, you know, MRI studies and the like very difficult to interpret, because if you average across a lot of people, what it means is you blur things out, you know, because you can only extract out the commonalities. And although, you know, they're getting better and better at dealing with that. So, okay, so there's other ways that you can think about the brain too. These are all approaches to understanding it. You know, I would say it's a very, very complex thing. In fact, it's the most complex thing there is. You know, there are more patterns of combinations of neural connections in your brain than there are subatomic particles in the universe. So you are, I know you won't believe that because it doesn't seem possible, but you can do the math and you'll figure out that it's actually right. So you're the most complicated thing there is, and by a lot. And so in some sense, there's more space inside your head than there is space outside your head. It depends on how you conceptualize space, you know, because you can conceptualize space as the number of ways that something can be configured, and that's state space. And that's a magnitude measurement, you know, and the distance between things, well, that's another way of conceptualizing space. But if you want to think about big, what's inside you is, I think that it's bigger than what's outside you. It's certainly that way in terms of complexity, unless you factor in the other brains. You know, so that's very much worth thinking about. It means that, you know, what we don't understand about the brain is going to fill many, many books. And one of the things we really don't understand is consciousness. People just don't get that. And it doesn't really look, you know, you might think that consciousness is an emergent, late evolutionary function, you know, but it doesn't really look like that. You know, I mean, even when people become demented and they lose almost all of their higher cortical function, there's no doubt that they're still conscious. And so consciousness might be way, way, way older than we think. And in fact, I think it's highly probable. I don't think a hypothalamic cat is unconscious. It's certainly awake, you know, and distinguishing between awake and conscious is no easy thing. You might say, well, animals aren't conscious. It's like, well, you know, here's the thing. You know, what people normally think is that humans are different than other animals, and so before you anthropomorphize an animal, you should be careful. But I think that's complete rubbish. I think it's exactly the opposite. Before you assume that humans have attributes that animals don't, you have to prove it. Because there's continuity. Tremendous, tremendous continuity. And so it's right to anthropomorphize animals. What's wrong is to presume a priori that humans are qualitatively different. Now, there are some very bizarre things about us, obviously. You know, we have opposable thumbs. That's a big deal. We can grip things. That's a massive deal, you know. And it turns out that there's another, your brain maps your body onto its surface, onto its motor strip and its sensory strip, which are roughly here on the brain. And if you take the motor strip or the sensory strip and you make a representation of how it represents the body, which is called a homunculus. Wilder Penfield did this first at McGill University. He I don't know if you know this, and perhaps you'll be fortunate enough to experience it, but people who have brain surgery are conscious when it happens. And that's so that the surgeons can figure out whether this little part is doing anything important before they take it out. You know, it's a very horrific thought. But Penfield, when he did some of the early psychosurgery for epilepsy, because in intractable epilepsy, sometimes the only thing to do is radical surgery, like he cut the corpus callosum, for example, so that the electrical storms, so to speak, can't transmit across the hemispheres and the whole brain won't be affected. But while he was doing that, he used a little electrode to map out the surface of the brain, and he mapped out the motor strip, which is just behind the prefrontal cortex, and then the sensory strip, which is just behind that, to find out how the body represented, or the brain represented the body. And basically what he showed was that